Hello everyone, this is a follow-up lecture of my new lecture series on guessing. As I mentioned before, guessing seems like a simple mathematical puzzle, but it can find many applications in our daily lives, and so we shall touch upon some of its applications later in the series as mentioned before. Today's focus will be more on the upper and lower bounds on the guessing moment. So we would be extending simple statistics like mean, we have already covered in our past lectures, to higher moments of the guesswork. And I'll have to point out that this new video series is a bit more sophisticated and advanced, so requires some background on information theory and some of the technical background we introduced in our previous lectures. So in our past lecture, we have come up with the generalized definition of Shannon's entropy and introduced Renyi's entropy, particularly for multiple symbol guesses, in other words, guessing a complete word of symbols, which led to this definition, the definition of Renyi's entropy. And surprisingly, as we shall see in this lecture, when we consider moments of guessing, we also end up with the characterization of upper and lower bounds expressed in terms of Renyi's entropy. I'd like to remind you the notation, which you may not remember from our past lecture, that we let x to be a random variable defined in a finite set x of size m. We call a function gx to be the guessing strategy or guessing function if g maps this finite set x to another set of elements 1 to m. So this mapping needs to be 1 to 1. We usually denote the optimal guessing function with g star x. I would like to also note the guessing number in this case is the expectation of the guessing function. One of the key results, in fact, the lower bound pertaining to the moments of guessing is obtained by Arikhan 1996. More specifically, he has shown that for any arbitrary guessing function gx and a positive row, the lower bound is given by the following expression as shown in this slide. We immediately realize that if you ignore the term in the beginning of this expression, this bound can be expressed in terms of Renyi's entropy. The proof for this lower bound can be obtained by several clever inequalities like Jensen's inequality and Hölder's inequality. And we also note that this result can be extensible to a word of size n, whereby each symbol is characterized by a random variable xi. So considering a word of symbol size n of symbols, so let us see how would this lower bound would look like in this special case. As can be seen, not much different. We have a multiplier n in the expression, as you can see. And Arikhan also introduces a shorthand notation for the probability term in the expression and names it expectation subscript rho x. So as can be seen, this notation is in fact a row fraction of the Renyi's entropy of order 1 over 1 plus rho. So we finally note that this result above for n IID random variables can readily be extended to different and dependent sequence of random variables, and the same lower bound now in terms of joint probability density function can be given. So for the details, I urge you to take a look at the Arikhan's paper. Okay, so let us consider the upper bound. First of all, we realize that the previous lower bound do not assume any particular guessing function. However, without assuming a particular guessing function, no useful upper bounds can be derived, and this was part of what Massey has concluded in his paper back in 1994. So let us suppose that we use the optimal guessing function, g star, that choose the elements of x in a non-increasing order of probabilities. So we note that this choice does not necessarily mean for a different choice of a guessing function, we cannot find any useful upper bounds. Actually, we can. And we will show that, this is possible. Upper bound can easily be expressed in terms of previously introduced expectation subscript rho x for the optimal guessing function. And we can also extend this result to n IID random variables as shown below. And finally, the asymptotics, show that bounds are tight for large n and can simply be expressed in terms of Renyi's entropy. So let us also talk about some of the extensions to Arikhan's main results. The primary extension to these results is provided Arikhan himself by introducing another random variable correlated with x, and he named it y, and explores the conditional guessing number. He figures out that the similar upper bounds can be given without much difference for this more general case, and he further demonstrates that such bounds can be applied to communication theory and sequential decoding in particular. And he basically characterizes the cutoff rate using these results. And however, the upper bound given for the optimal guessing strategy seems to be too restrictive. And in non-asymptotical region, it might not be very useful. That's the first thing that we realize. The secondly, guessing functions other than the optimal wouldn't be able to use this bound. It turns out that a tighter upper bound can be given for the integer moments of the guessing number used with the optimal guessing strategy. Moreover, this new upper bound also applies to a set of guessing strategy other than the optimal. That is the more precisely for a given probability distribution P, which has P1 to Pm for any positive integer m and any r greater than or equal to 1. If we have this inequality shown in 1, then we would satisfy the condition and the mth moment of the number of guesses would satisfy the expression given below. So we note that such an inequality would be satisfied for a monotone distribution as well, but a subset of non-monotone distributions may also satisfy this inequality. So under this condition, the mth moment of the guessing satisfies this recursive upper bound given below. In other words, the mth moment of the guessing can be upper bounded by all lower bounds of guessing, the same random variable. That's the bottom line. Guessing function may or may not be optimal in this case. That's why we don't have G star, because there's a condition, for the probability distribution, and we are basically guessing the first, indexed item and then the second index item and the third index item. If it is non-monotone, then the guessing function wouldn't be optimal, for example. So one of the restrictions with this result is that Bose-Stach result only is applicable to integer moments. Okay, in other words, m is an integer value. So the proof of Bose-Stach result is based on the following simple observation for a probability distribution defined on set x, that the exponential of expectation subscript r minus 1 x can be lower bounded with the following weighted probabilities as shown. And for comparison purposes, we provided those bounds for m equals 2 and m equals 3. At the end of the slide, as we shall see numerically, and we'll also see that numerically later, Bose-Stach results would be tighter in the non-asymptotic regime. So there have been some recent efforts to improve bounds in the non-asymptotic regime. A notable and recent study is by Sasson and Verdu. Based on their analysis, both lower and upper bounds can be improved. Though bounds become more complicated to express, as you can see, they become more useful in the non-asymptotic region. The lower bound they have derived is given as shown below here. As you can see, it's in terms of a supremum, in other words, a beta value that maximizes the expression. Furthermore, a function is defined in terms of beta value, and for different beta values, it has a different form. So as you can see, it becomes more and more complicated. The expression becomes more complicated. However, it becomes more tighter, as we shall see using a numerical example. Since this bound is more general, it can be reduced to Oricon's lower bound by selecting this beta value, setting beta value to 1. The same study also provides multiple improved upper bounds, such as the one shown in this slide on top. It is shown that this upper bound can be improved even further if we consider different range of rho values individually. For instance, if rho is between 0 and 2, this bound would correspond to m equals 0 and 1 and 2 cases in Bose-Stach analysis. And the upper bounds actually match with this study and Bose-Stach study. As for rho greater than 2, the same line of work improves the bound shown above, and it gets really close to Bose-Stach for integer values of rho. However, it turns out that Bose-Stach bounds, though restrictive to integer moments, are still the best as of today. And I urge you to take a look at the original paper, which covers the details and the proofs. Okay, so it's better, I think, to consider a numerical example to illustrate how these upper and lower bounds play out with each other. We assume a geometrically distributed random variable with finite support. So the set of available or possible values contains 32 elements, and the probabilities are parameterized by a value, a variable a, which is set to 0.9 for this example, and we compute 1/3 natural logarithm of the expectation of the third moment of guessing for this particular example. The lower and upper bounds as well as the exact value are given in the following table. As you can see, the Sasson's lower and upper bounds are closer to the exact value compared to Oricon's asymptotically tight results. And furthermore, Bostage's upper bound is seen to be better, though the difference between Sasson is pretty small. And this gap can further be explored through different probability distributions, guessing functions, and moments. But I'd like to also point out Bostage's results are only restricted to integer moments, okay? But Sasson's results are more general, and they are very, very close, as I'll show you in this next slide. Here's the plot for various moment orders for different upper bounds on the moments of guessing. Oricon's upper bound is quite close as the order of moments increase. However, in the non-asymptotic regime, its estimation is a bit far from the actual value. On the other hand, Bostage and Sasson's bounds are observed to be very, very, very close, and Bostage is tighter. That's what we observe from those plots. Okay, however, there seems to be still a gap between the actual value and the available upper bounds in the non-asymptotic regime, considering those moments of guessing. In other words, for example, 10th moment or less are more useful usually in our practical applications, so better upper bounds can further be investigated. Anyways, in this lecture we considered bounds on the guessing number and their improved versions. We concluded that there's still room for improvements for the non-asymptotic regime. There are a few more questions that come to mind around the idea of overall guesswork. How about some side information is available before we make each guess attempt? How about each choice we make have a certain cost other than the guessing number, guessing order? And also, how about the guesser chooses to stop guessing at the expense of some cost and asks for the answer directly? So these questions are partially answered by the studies we mentioned about it, today in today's lecture, and few more recent studies touched upon cost of guessing and also the application of Smoot-Renier entropy, for example, to the third question. We'll explore those approaches in our future lectures. Clearly, analysis will require different approaches and tools to tackle such questions, and variety of answers are still yet to be found. So thank you for listening to today's lecture.